Okay, in the earlier talks I have talked about electric current, its properties, its SI unit, and somewhere in the talk I also mentioned something about potential. I mentioned the term potential. Now we'll be doing details about this electric potential. Now what is potential? It is simply a property of an object or two objects which will determine the direction of flow of current. Like I had two bodies A and B, and charges were flowing from one body to the other body. Now what is potential? It is simply the property of these two bodies which determine what will be the direction of flow of charges. So a proper definition of electric potential, it is given in this way. It is the amount of work done in bringing a unit positive charge from infinity to a point in an electric field. I have a unit positive charge in infinity, and I'm trying to bring this unit positive charge from infinity to a point in an electric field. And when I do so, I cannot simply do it. When I try to change the position of this unit positive charge at infinity, I need to spend some energy, and the energy that I am spending, that is known as your electric potential. So what I mean is, like in a diagram, I have a point A in a field, in an electric field, and I have a unit positive charge somewhere at infinity. What is infinity? A point which is very far away from point A. I cannot measure the distance between the point or between the charge and this point A. What I am doing, I am bringing this unit positive charge from infinity to this point A. And then, as I told you, when I do so, I have to spend some energy, and the energy that I am spending, that energy is termed as the electric potential. Unit of electric potential is volt. V-O-L-T, and it is denoted by the letter capital V. Again, there is another term, potential difference, related to electric potential. Now in this case, I have 2 points. I have a point A and I have a point B, such that the distance between these 2 points can be measured. They are at a finite distance. In this case, what I am doing, I have a unit positive charge in here, I am moving this unit positive charge from point A to point B. Again, when I do so, I need to spend some energy, and that energy is known as the electric potential or potential difference between these 2 points A and B. So basically, it sounds similar, both of them sound to be same, but what is the difference between them? In this case, I am bringing from infinity. In this case, the distance between the 2 points is finite. I know this distance. I know the distance between point A and point B. This is a finite distance. So, the mathematical representation of potential difference, it is given by this V is equal to W by Q, where V is the potential difference, W is the work done, and Q is the charge moved. What I mean in here is this. I have Q amount of charge in point A. I want to move this Q amount of charge from point A to point B. When I do so, when I am moving this charge, I need to waste, or I need to spend this much amount of energy. That is, I need to do W amount of work. So the potential difference between point A and point B, it is given by V is equal to W by Q. SI unit of potential difference is 1 volt. So another important concept that we need to know for numericals, I'll do this. Okay. Suppose I have these 2 points, point A and point B, and I have a charge somewhere in here, and this charge, this positive charge, it is at infinity. I have a unit positive charge at infinity. Now the amount of work done to bring this unit positive charge to point A, it is the potential, electric potential at point A. I am representing this by V of A. And the amount of work done to bring this unit positive charge to point B, the same unit positive charge from this point at infinity to point B. Suppose I am representing the work done or the electric potential by VB. Again, the potential difference between point A and point B can be represented by this. I have suppose V, the electric potential difference between point A and point B, I can write this as V of A minus V of B. So these are the things we need to know for numericals. This is an important formula. We need this, and also I need this. In some numericals, you have to use this concept. Okay, coming to the unit, it is 1 volt represented by V. Now again an important question from the exam point of view, it is this, the definition of 1 volt. The definition of 1 volt. What does 1 volt mean? As we have done for 1 ampere, we will do the same in here. What I am doing, I am putting W to be 1 joule, the unit of work done, it is joule. And I am putting Q to be 1 coulomb. So now from this formula I have V is equal to 1 joule by 1 coulomb. So I have my V is equal to, the potential difference is equal to 1 volt. So what is 1 volt? It is the amount of work done. Or what is 1 volt? It is the potential difference when 1 joule of work is done to move 1 coulomb of charge from one point to another. I hope it is okay. Again I am repeating. What is 1 volt? It is the amount, it is the potential difference between 2 points when 1 joule of work is done to move 1 coulomb of charge from one point to the other. Like if I have 2 points, I have point A and point B. When will my volt potential difference between these 2 points will be 1 volt? If I have 1 coulomb of charge in here, and the amount of work done to move this charge, this 1 coulomb of charge from point A to point B is equal to 1 joule. So this is an important, definition. Another definition, it can be given in this way: if 1 joule of work is done to bring a unit positive charge from infinity to a particular point, that is again 1 volt. So the next topic, the next point we should remember is voltmeter. What is voltmeter? A voltmeter is a device which is used to measure or detect electric potential. Just like we had ammeter. What was ammeter? It is a device which is used to detect or measure electric current. Similarly, what is a voltmeter? A voltmeter is a device which is used to detect or measure electric potential. Now again, another thing you should keep in mind, it is that voltmeter is always connected in parallel. Voltmeter should always be connected in parallel with the circuit. Okay, so we have discussed about electric potential in our talk. Now an interesting question that arises in our mind is, how does electric charge flows through a conductor? I have explained why electric charge flows through a conductor. Now we are talking about this, we are looking at this question, how does electric charge flows through a conductor? See, I have 2 diagrams in here, I have 2 figures in here. I have this is a conductor, and this is also a conductor, the same conductor. If you notice one thing in here, the electrons are not aligned in a manner. I mean, the electron can freely move in any direction. Like in this case, the first electron is moving in this direction, this electron is moving in this direction, this electron is moving in some other direction. So basically, the movement of electron is not it is not moving in a specific direction. Why? Because this conductor is not connected with an electric source or a potential difference. Now, in here, if you notice, all the electrons are flowing in the same direction. Why so? Because this conductor, I am connecting with some source of potential difference. In this case, my source of potential difference is a battery or a cell. So as soon as I connect this battery with this conductor, these electrons will align themselves in a particular direction. What I mean is, because this is for a positive terminal, all the electrons will be aligned towards, or will try to move towards the negative terminal. So this is how electric charge flows through a conductor. As soon as I have some source connected to this conductor, these electrons will align themselves in a particular direction. Now, see, this electric current will flow through this conductor only when I have a potential difference in here. What I mean is this: I have suppose I have two bodies. I have a body A and I have a body B. I connect these two bodies. If this is positive, this is negative, the conventional direction of current is from point A to B. Charges will flow from point A to point B. But this charge will continue, this flow of charge will continue as long as there is a potential difference. If body A and body B are at the same potential difference, or is at the same potential, the flow of charge will stop. So how to maintain a constant potential, or the more important question is, why should we maintain a potential difference, a constant potential difference, in order for charges to move from one body to the other body. So how do we do this? We do this by using certain devices. Like we can use, many devices are there. We can use a battery which by the help of some chemical reaction will maintain the terminals of a conductor, or will help maintaining the terminals of a conductor at potential difference with some constant potential difference. Another method of maintaining constant potential difference is by using an electric generator. So these two devices, the first is your battery or cell, this device, and I have the next one is the electric generator. These two devices are worth mentioning. Why? Because these two devices helps maintaining a constant potential difference between the terminals of a conductor. A cell will convert, how does a cell maintains a constant potential difference? By converting chemical energy into electrical energy. So my cell will convert chemical energy to electrical energy, or in other words, there are some reactions going on in the battery which will maintain it in a constant potential difference, and your electric generator will do some mechanical work, or it will convert mechanical energy into electrical energy. Okay, the next topic that we'll start with, it is an important topic. We have Ohm's Law. Now what is Ohm's Law? It says the amount of current flowing through a conductor is directly proportional to the potential difference maintained at its end, provided all the physical conditions remain same. So what I mean in here is this: I have a conductor, suppose this is my conductor, and this is connected with some potential difference. Now because of this potential difference, a certain amount of current will flow through it. Suppose the amount of current flowing through it is I. What Ohm's law says us, it says us that this current I, it is directly proportional to the potential difference maintained at its end. So the potential, if V is my potential difference, my I is directly proportional to V. Now what I mean by this sign directly proportional, it means if I increase the potential difference, it will increase the current. If I increase, suppose my potential difference is 1.5 volt. I have certain amount of current. Second case, if I increase my potential difference to suppose 2 volt. According to this law, it says if I increase the potential difference, my second current, if it is I2, it will increase. That means my I2 has to be greater than I1. Again I am repeating, I have in the first case I am keeping fixed my potential difference to be 1.5 volt, and suppose the current in this case is I1. I am changing the potential difference now. I am increasing the potential difference to be 2 volt, and correspondingly I am getting a current. I am denoting this by I2. What this law says, it says that the amount of current, it directly depends on the potential difference. So if I increase the voltage, if I increase the potential difference, my current will also increase. So my I2 has to be greater than I1. What if I decrease this? Suppose in the next case, I am putting my potential difference to be 1 volt. So I have decreased the potential difference. When I do so, if my corresponding current is I3, the current will correspondingly decrease. So what I have my I3, it is less than I2, which is greater than I1. Because the minimum voltage is 1 volt, correspondingly I am getting a current I3, this will be the minimum current that I am getting. So this is a very important law which we need like later on in the numericals as well. Now this law, it holds for as long as the physical conditions are same. What I mean by physical condition, I have mentioned this, like this condition holds as long as the physical condition remains same. What are these physical conditions? It means the temperature of the conductor, the length of the wire, the area of cross section remaining, like if I keep this fixed, then only this Ohm's law will hold. If I change this Ohm's law, or this result, it may not hold. Again, Ohm's law fails in these certain conditions. The first condition I have, if the temperature of the conductor increases, Ohm's law fails. Now again, in some cases, in some applications of, in some appliances of electricity, we have certain devices which sets off magnetic field, like we'll be discussing this in the next chapter. So again, in those cases, for those appliances, your Ohm's law fails. I cannot, like this law is not valid for these cases. Again, Ohm's law will fail for some semiconducting material like your diode, your LED, all these materials. For all these materials, my Ohm's law fails. Now, in here I have this condition, I have I is directly proportional to V. I can also write this as V is directly proportional to I. This is my Ohm's law. So when I remove this proportionality sign, I need to introduce a constant of proportionality. So in this case, I am introducing this constant of proportionality denoted by R. So I have V is equal to IR. I can also write this as V is equal to RI. This R is a constant of proportionality. Constant of proportionality, and it is known as resistance. This is a very important topic that we'll do later on. This constant of proportionality in here, it is known as resistance. So from Ohm's law, I am introducing another important concept in here, and which is resistance. So from Ohm's law, what is resistance? It is nothing but the constant of proportionality which appears when I remove this proportional sign in here. Now, what is this resistance actually? It is a property of a body by the virtue of which it tries to resist the flow of electric current through it. So what is resistance? The proper definition, it is given by this. It is a property of a body by the virtue of which it will try to resist electric current flowing through it. So let us take an example. I have a material in here, I have a conductor in here, and charges are flowing in this direction. So what is the, what is resistance in here? This resistance will try to oppose this flow. Instead of, it will not allow electric current or this charge, it will try to oppose, it will try to resist, it will try to stop electric current flowing from it. Unit of resistance, it is given by ohm, denoted by the symbol omega. Okay, we have talked about resistance. What is resistance? As I told you, it is a property of a material by the virtue of which it tries to oppose the flow of electric current through it. Now there are various factors affecting resistance of a conductor. The first property is your length. Resistance of a conductor or of a material depends directly upon length. My resistance is directly proportional to the length of the conductor. What it means? It means if I increase the length of a conductor, the resistance will increase. If I decrease the length of the conductor, the resistance will decrease. Another factor which affects the resistance of a material is the area of cross section. Now, what is area of a cross section? Usually, conductors, it is cylindrical in shape. Generally, not all the time, but I am taking this to be cylindrical in shape. So, what is area of cross section? It is the area of this region. Okay, so if this is my conductor, my area of cross section will be the area of this region, of this base. So the resistance of a conductor is inversely proportional to the area of cross section. So inversely proportional to the area of cross section. We have already discussed what directly proportional means. Inversely proportional, it means something like this. If I increase the area, the resistance will get decreased. If I decrease the area, the resistance will get increased. Another factor which affects the resistance, it is the nature of material. Certain material, they offer a very high resistance. Certain other materials, they offer very low resistance, like your copper or silver, they offer low resistance, whereas there are certain materials like your nichrome wire which offers high resistance. Then I have temperature. Now it is said that resistance usually increases with the increase in temperature, but there are certain exceptions. Usually for most of the metal this is true. With the rise in temperature, the resistance increases. But for semiconducting diodes, this condition it may not hold. Or for some alloys, this condition it doesn't hold. That means for alloys, with the rise in temperature, the resistance will generally decrease. Now, these two factors which affects resistance of a material, that is, the first is my length, which is directly proportional, and the second is my area, which is inversely proportional. So I am taking these two equations and I am combining them. So what I am getting? I am getting this. I have R is directly proportional to L by A. When I combine equation 1 and equation 2, I have R is directly proportional to L by A. Again, I am removing this constant of proportionality. So what I have done for Ohm's law, I have to do the same. I have to introduce a constant of proportionality in here. I am removing this proportional sign in here. So what I have to do, I have to introduce a constant of proportionality in here. So this is my constant of proportionality. I have rho L by A. Again, an important topic comes, an important term comes out in here. This is my constant of proportionality. This constant of proportionality, it is known as resistivity. Of a material or specific resistance of the material. So the specific resistance or resistivity is denoted by this symbol known as rho. So we'll look at this in detail. So I have my R, this is equal to rho L by A. What I am interested in this specific resistivity. So what I am doing, I am keeping resistivity, specific resistance in one side and shifting all the other terms in the other side. So I have R A by L, this is equal to rho, or I can write this as rho is equal to R A by L. Now I am putting these terms, I am fixing the value of A and L. I am putting the area of cross section for this particular material to be 1 meter squared and my length of the material to be 1 meter. When I do so, this expression will change like this. I have rho is equal to R. So from here I am getting the definition of specific resistivity. What is specific resistivity? It is the resistance of a substance which, like the resistance offered by a substance of whose area is 1 meter squared and length is 1 meter. So I have a material whose area of cross section is 1 meter squared, the area is 1 meter squared and the length is 1 meter. Now being a conductor, it will offer some resistance. Now that particular resistance offered by this type of material whose area of cross section is 1 meter squared and the length is 1 meter, that resistance is known as your specific resistivity. Now it is important for us to note one thing, is that different materials will provide us different specific resistances. We'll look into details again to the values and then we'll draw out some conclusion depending on the values of these specific resistances. Now earlier I have mentioned about the unit of resistance to be ohm. From this unit I can also find out the unit of rho, my specific resistance. So what will be the unit of specific resistance? What I am doing, from this expression in here, I am using this expression to find out the unit of specific resistance. What I do, I put my rho, the unit of rho will be something like this. I put the unit of the various variables that are in here, the various the various physical quantities that are here. The unit of resistance is ohm, the unit of area is meter squared, and the unit of length is meter. So from here you can see that meter and meter square get cancelled, so I have ohm meter. So basically what is the unit of specific resistance? It is ohm meter. So keep this in mind. The SI unit of specific resistance, or I am denoting this by rho, it is ohm meter. Okay. And the CGS unit of rho, the CGS unit is I have ohm centimeter. CGS unit is basically a smaller unit for rho. So the definition of 1 ohm, this is an important topic from the exam point of view. So what is 1 ohm? From Ohm's law, I know what is my what is Ohm's law? I have V is equal to IR. I'm interested in finding out the unit of, I'm interested in resistance. So what I'm doing, I'm putting resistance in one part and shifting everything else in the other part. So I have V by I is equal to R, or R I can write this as V by I. Now when will resistance be 1 ohm? When my potential difference is 1 volt and my current is 1 ampere. So what I'm doing, I'm putting my potential difference to be 1 volt and my electric current to be 1 ampere. And when I do so, I have my resistance is equal to 1 ohm. So from here I am getting the definition of 1 ohm. What is 1 ohm? It is the resistance offered by a conductor when 1 ampere of current flows through the conductor, maintained at an electric potential of 1 volt. So this is the definition of electric current. Keep these definitions in mind. Okay, we have looked at the definition or general definition of conductors and insulators. Now let's just go a bit deep into it. What are conductors? I have told earlier that it is materials which will allow electric current to flow through it easily. Now, with respect to resistance, what a conductor is? A conductor is a material which will offer a very less resistance or a very low resistance to the flow of electric current. What is an insulator? An insulator is an object which offers a very high amount of resistance such that electric current cannot flow through these materials. Now in between these conductors and insulators, there is another term that we'll be using, that is your resistor. Resistors. What are resistors? These are simply devices which exert some resistance to the flow of electric current. Okay, most of the metals are considered to be conductors. Why? Because they have free electrons in them. But there are exceptions like your tungsten and your platinum, and most of the non-metals are considered to be insulators. But there are again exceptions like your graphite. Okay, in here I am talking about two conductors or two materials. One is your silver, which is it is the best conductor of electric current, and another material in here is nichrome. This is an alloy which is used as a heating material in various appliances like your heaters, your irons and all. And I am looking at these are my specific resistivity of these two materials. So I have silver. The specific resistivity of silver is 1.6 into 10 to the power minus 8. And the specific resistivity of nichrome, it is 1 into 10 to the power minus 4. Now if you look in here, this value is very small compared to this value. So what I am trying to focus in here is that when the value of specific resistance is small, my resistance is less, and this material will become a good conductor of electricity. And there will be less heating. The heating effect will be very less. Whereas if the specific resistivity is more, like in this case of nichrome, this resistance will be more and the current flowing through it will be less, and correspondingly the heating effect due to this material will be very large. So keep this point, these points in mind. If my specific resistance is less, this implies that the material is a good conductor. It's a good conductor of current. Like for example, I have silver, which is a good conductor of electric current. And if my specific resistance is more, then this becomes a good resistor. The resistance, it has a very high resistance. So this would imply that this particular material with specific whose specific resistivity is more is a poor conductor of electricity. So with this we have completed the part with the specific resistivity.